Okay, good afternoon, everyone. So we are resuming the colloquium program with Professor Craven. Tom Craven is one of our own faculty here in the Department of Physics and Astronomy. He specializes in space physics, and he came to Kansas in 88, yes. And before that, he got his PhD at Harvard and did several research programs. Particularly, he's member of many associations and scientific associations and fellow as well of some of them, including the AAAS. No. Well, the web page says that.
American Geophysical Union.
Ah, yeah, really.
AGU.
I apologize. So then, okay, but Professor Craven is a very distinguished physicist with us, and I'm very happy to have here in the colloquium. In particular, today is a special moment because it's the anniversary, right, of the celebration of the Cassini mission. No?
It's further.
Sorry, I don't. Okay, thank you very much.
It's a wake. Yeah, and it was a cremation, not a burial. Okay, thank you. Those who were in the Astro, I gave an earlier version of that there, so sorry. Add a few little extras, okay? And it's going to be mostly historical. I'll throw a little science there, a little my science, but with a little luck, I'll run out of time and you won't have to hear it, okay? Or you could hear it some other time, okay? And the science is still developing. Those who have been here the, quarter of a century or more that I have actually heard bits and pieces along the way, depending when you arrived. Some who have been around a particularly long time, Bruce, Steve, Barbara too, and Phil. You have heard early parts of it, but I'm sure you do not remember what I talked about 20 years ago. So I found a bunch of stuff from over the years involving this mission, threw it in there, and then have taken the stuff that has just happened in, say, the last year, and we'll emphasize that. So, the mission, and I'll start with the history. Again, it's a big spacecraft. The orbiter is about the size of a school bus. It is, it's got a long magnetometer boom. Fully fueled, it was about 6,000 kilograms, and is now it's non-existent now, but in August it was much lighter. The cost in about $1990 was about, $3 billion. That does not include operational costs. Some of that was built from the Europeans. So it was a joint NASA European Space Agency mission. They built the probe, the Huygens Probe. The Italians built the high gain antenna, and said it was a joint effort. Had two big engines, unlike the Voyager spacecraft, which flew by Jupiter and Saturn, but didn't linger in the Pioneer spacecraft. In order to go into orbit, you're going to have to light up a main engine and get rid of energy and angular momentum. This did. The power was from three RTGs, radioisotope thermoelectric generators, plutonium oxide, which had thermocouples and provided electricity. About 900 watts was the total power output. So the whole spacecraft, communications, everything had to exist on about a kilowatt. It was about 25% less than that at the end of the mission. And again, there's the probe. So I'll go through a little bit of history. 1982, the European Space Agency, ESA, and the National Academy of Science had some joint discussions of doing a joint European-US mission, which had not happened up to that point. ESA was still fairly young. NASA was born in the late 50s, ESA later, I forget the date. And a working group was formed. You know, you want to figure out what to do, you form a committee. And so there was a committee, then other committees, and it's basically, because it costs money, it's lots of politics. So there was lots of politics for a while. In 1983, the NASA Solar System Subcommittee recommended the mission. And then following that for a few years, many studies, mission concepts, etc. That's the sort of thing the SSC does. I remember being on it a few years ago, and the big issue was the cost overruns on Curiosity, and what we could do about it. The answer was nothing. It was too far along. It was going to be launched. Okay. Also, the other issue was James Webb was eating everyone else's lunch. And how to protect ourselves, meaning planetary, from the astrophysicist. Sorry, that was a priority for us. So in 1988, the NASA Associate Administrator for Science, Len Fisk, and ESA's Roger Bonnet agreed to pursue this. So it got a little more familiar. And it went and then Congress approved a Mariner Mark II concept, meaning to have one spacecraft do a lot of different things in the outer solar system. One design. It'll be cheaper, better, just like the, similar to what they had in mind for the shuttle. One thing to do many things. And there were going to be two missions, initial missions, Cassini to the Saturn Titan system, and a Comet Rendezvous asteroid flyby mission. You realize this is after the 1986 Halley encounters of several spacecraft, the European Giotto mission, the Japanese Sakigake and Suisei, and the Russian Vega 1 and 2 missions to Comet Halley. So they wanted to go back and go to an asteroid with essentially the same spacecraft. So in principle, it was a good idea. Of course, it involved a considerable commitment and time. Okay, the mixed and personal history. I arrived at KU from Michigan, and I was very interested in comets at Michigan. So as we built up to the 1990 period, I did start to do some modeling on Titan and the Saturn system with a graduate student I brought with me from Michigan, Lou Gann, and with Ned Keller, who some of the older people might remember here, who was actually had a chemistry undergraduate degree. And we started doing models of Titan, thinking ahead. Also, I joined a Jet Propulsion Lab proposal being put together by Marcia Neugebauer, who was actually one of the discoverers of the solar wind back in '62 on the Mariner 2. She was nearing the end of her career, and we joined in. I knew her from the comet encounters, and I got on an electron spectrometer instrument as a co-investigator. Electron and ion spectrometer, measuring electrons and ions between a few eV and some about 20 keV. And then there were instrument selections where I was part of that. Well, and so much for that. In 1992, the whole concept ran into problems with Congress, and the plug was pulled on it. And NASA managed to salvage the Cassini part, but Kraft was outright canceled, to the chagrin of many, and I was one of those many. Okay, but when one door closes, sometimes, but not always, another door opens. So no longer being involved in a electron spectrometer going to a comet, there was one more opportunity on Cassini. Most of the instruments were chosen, set, but there was no mass spectrometer on board the orbiter. There was a gas chromatograph. No, there was a mass spectrometer on the Huygens Probe being built at Goddard Space Flight Center, but not one on the orbiter. It was decided, and rightfully so, that if you're going to go through the atmosphere of Titan, and you're going to go through some other atmospheres, you need a mass spectrometer. So the Goddard agreed to build it, but didn't want to do the science, so they opened up a competition for a science team, about 6 of us. Well, I applied. I mean, comets were dead. Obviously, you got to go with the flow, The flow was towards Saturn. So proposed and got it, which meant that for about 8 years, I got almost no money and went to lots of meetings because the money was all going to cutting metal, and did a lot of arguing, but did do a lot of modeling with a number of students to sort of prepare for that. So in the early 90s, there were instrument designs and constructions and, testing and all that sort of stuff. Another crisis. In 94, they almost canceled Cassini, too. But they really couldn't, because they were trying to preserve good relationships with ESA and the Europeans, and it would have sort of meant a permanent halt to that, or at least for a very long time. And politically, that was difficult, which was very fortunate, because it means the mission scraped by, but they had to de-scope it to try to, quote, make it cheaper, and they removed the instrument scan platform to save about $100 million or so. Well, I think we've spent about $400 or $500 million since then just for the more expensive operation of the spacecraft, and created all sorts of troubles and arguments and meetings over a decade and a half, particularly between the mass spectrometer team and the radar team, because we each wanted to control where the spacecraft was pointing. The scan platform would have eliminated that, yeah? But hey, at least the mission didn't get canceled, yeah? And a lot of little drama there. Instruments were supposed to be delivered at some date to Jet Propulsion Lab to be integrated with the spacecraft, which would then be shipped to the Cape. Well, our instrument didn't get shipped to JPL. And I say the end of 96, early 97, there's going to have an important shake test. They said, do you want to go see it? And I said, sure. So I went to Goddard, and we went in a booth, and the instrument went this and this and all that. And then the chief engineer, all of a sudden during one of the tests, said, oops, instrument just died. The signal totally disappeared. Evidently one of the little leads inside the spectrometer broke under one of the shakes. Which meant they had to open up the instrument, fix it. But then the trouble with these things is you got to evacuate it, bake it. It takes about 3 weeks to get it back to the starting point that you could do it. So it missed, well, fortunately it didn't totally miss the boat, By the way, it was not my fault, later when they're looking at it, playing with it, I was allowed to look at it and peer, but I was not allowed to touch it. Which somehow they had found out what happened when I was a first-year graduate student in the Tumble Level physics lab, but I don't know how they knew that, but it was probably wise, That's another story, okay? Why I became a modeler and not an experimentalist, So it was delivered finally right to the Cape and integrated with the orbiter, fortunately. Then there was a successful launch in October 1997. Took about 3 tries, because of weather conditions, other things, not unusual. It was a night launch. There was an initial delay to the end of the window because the Titan 4B had been redesigned, and it blew up with a payload, an Air Force payload. It was an Air Force vehicle. And they did not want to put this several billion-dollar spacecraft on it till they had had one successful launch prior to this launch. So they had the successful launch to say, go ahead. And we all then gathered around and maneuvered around there are a lot of protesters too because of the plutonium on board. They're afraid of that thing crashing, burning up, and doing stuff to people. Although this stuff was very safe. It's not. They think weapons grade plutonium. This is plutonium oxide. You can hold it. In fact, we were passing around a pellet at one of the meetings. It's warm. But it's not. Oh, it is dangerous if you chew on it. Okay, so don't give it to any toddlers. Okay, so then I had a 7-year journey, orbit insertion, etc. I'll say a little bit more about that. The probe another milestone. The probe entered Titan's atmosphere in 2005, and then it ended. Okay. Okay, so there's, and as I said, the long timers here have seen this many times. Okay. If they remember it. That's the spacecraft, that's the Huygens Probe, that's the high gain antenna. INMS, there's about 12 instruments, but I'm very focused on one in particular, okay? Bias, you would call it. There's the one of the RTGs. There's a magnetometer boom. You want to get the magnetometer far from the spacecraft because of the contamination fields. There is the spacecraft sitting at the Cape, sitting on top of the booster. There's a little shed up there on top of all this, what they call the stack. I mean, there's this, then there's the Centaur upper stage, then there's the Titan IV underneath it. And you could get a feeling for the size of this thing. Really exciting, our instrument design. We have a closed source where neutral gas goes into an antechamber. Due to Ram effect, you get about a factor of 50 enhancement. You bleed it off. Electron filament ionizes it so you could control it, and then it's put down through some radio frequency quadrupole lenses, which selects by mass, and you basically count. Click, 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 how many you got. And you calibrate it. Open source, nothing touches anything, so you come in there, you electrostatically, it turns the corner and goes down. And we use that, you could use it for neutrals, or that's how we measure ions. Just showing the same type of thing. Okay, there's the vehicle, photograph taken before launch. It's sitting up there under the shroud somewhere. Center upper stage right here. There's the shroud, there's the solid state strap-ons. And so we get up at about 3 a.m. 3 nights in a row. I'm getting a little irritable. Radar and INMS argues during the meetings in the day who's going to control the spacecraft 7 years from then when it actually arrives, okay? But finally it goes off, and it is a beautiful launch, and everyone is relieved. About as close as you get is about 7 miles away. There's a set of bunkers. As I told the anecdote, I went another 3 miles to a condo on Cocoa Beach, where we had a bunch of libations sitting inside and could watch NASA TV. And you could see a beautiful view with binoculars, a thing just sitting there, because you could look across the water. And it came up actually right across from us and over us, and great view, and you could see it go through the cloud and lit up the whole cloud. And then if you look with binoculars, you look, and you could see the tail flare for about 15 minutes if you look with binoculars. Then it finally disappeared. Finally, and then in that case, you go in and watch TV and you drink, and then and they give you the report, and then over the Indian Ocean, the Centaur upper stage lit up, and after about half of Earth orbit, it went into an escape trajectory. So it never did a complete orbit. It just launched out onto escape, and it did the loop-to-loop for a few years, because even with that booster and the Centaur upper stage, which is hydrogen burning and is very efficient, not enough energy to get to the outer solar system, to climb out of the gravitational well. So they did 2 close Venus encounters, a close Earth encounter, and used sort of the handball effect to gain energy and angular momentum that looped it out, a Jupiter correction, and then it arrived 7 years later. As a comparison, the New Horizons to Pluto went 3 times as far in 7 years. But on the other hand, it was about, about the size of a sofa, not the size of a school bus. And it didn't have a magnetometer.
You're still upset about that.
Yeah, really. It's like flying blind, okay? Yeah. But there you have it, okay? And the Pluto people didn't give me money either, so. Again, often shown, one of the first pictures from this spacecraft as it went into the system of the rings of Saturn, which are very intricate. And then you see the shadow of Saturn on the rings. Again, I'll go through it pretty quick. Okay, when it arrived, it had to light up its engines. So it had to get fairly close to the planet. So it maneuvered its high gain antenna into the ring plane, went between the F ring and the G ring, used the main antenna as a dust shield, and then flipped around, fired its main engines for this period of time. Had to be a 90-minute fire. And then it had to stop its engines right here to get into the orbit it wanted. And then as it went back through this gap here, it had to reorient its high gain antenna as a dust shield again. And then thereafter, it got to about 0.3 Saturn radii right there. And until a year ago, the closest it got was 3 Saturn radii. They did not want to get too close to the rings thereafter. Putting it through the satellite atmospheres, remotely studying the planet with all infrared, ultraviolet, visible, radio, and basically the whole spectrum. They were looking at the planet, but they didn't want to get too close. And looking at the rings and looking at the satellites. But it did allow an opportunity to make some in situ measurements of what was over the rings, including our instrument. So this is looking the other way, came through, did the burn, and then I put this big arrow here because that's where our instrument opened up right here. Our instrument was capped off for 7 years. Magnetometer, the particle detectors were measuring at Jupiter and the interplanetary media, a lot of interesting stuff out there. We had to remain capped off because we didn't want, when the main engines to going, to put all the junk into the mass spectrometer, and that's all we'd be seeing for the rest of the mission. So it had a cap, explosively burnt off, opened up when we saw, are we going to see anything? Well, we knew we were seeing calibration gas previous to that, and we did see something, which I will not talk about really. We saw O2 plus and O plus ions and protons, what we call the ring ionosphere. Okay, that was in Pasadena when it happened. So again, these things are every once in a while you have a big party. So we had the launch party. We went to Pasadena to look at this. And the control room was small, so most of us have to go somewhere else and look by closed circuits. So we were looking at closed circuits. And what you see here is the radio signal. And what this first little break tells you is that the speed is changing. What you're seeing is the speed of the spacecraft. You've seen the Doppler shift, basically. You've seen a frequency change. And all via the low gain antenna, because the high gain antenna is doing something else. So it's a low. And you're not, and then at this point where the other break is where the firing ended. So a successful starter burn, a successful end burn, and everyone cheered, and actually people had brought some of the family members to this. They did want to make it a party. They were assuming it was going to succeed, and it did. I brought Jeff, so we all had a good time. Well, we'll leave it at that. We had a good time. And stayed up late. And the engineers were hard working at collecting the data. And, so I got a call about 4 a.m. that I had to go to JPL fast because we actually saw something and the instrument was working. So I dragged myself out of bed and went to JPL, and it was exciting. We saw our first spectrum from the mass spectrometer, and it was something that sort of made sense. Okay, so Saturn, distance from the sun, 9.5 astronomical units. Light travel time, 84 minutes. So all these things that it was doing was choreographed by the computer, onboard computer. And because you either put the instructions in correctly or you did not, okay? Very simple. It's a radius of about 10 Earth radii. It's a big planet. Not quite as big as Jupiter, but big. Jupiter is 70,000. No surface, it's a gas giant. Mostly H2, molecular hydrogen, a few percent helium, maybe a part in 10,000 of methane, ammonia, a little water if you go deep enough in terms of clouds, and has clouds, contaminants which give it color, but mostly ammonia, water, ice. Rotation in about 10 hours. It rotates more rapidly than, Okay, so what is it? Let's see, more rings. Lots of ring photos over the years, okay? And you can see the Cassini division right there. You got the B ring right here. And the sort of what we were studying was basically this system. A lot on Titan, which is this is a relative size. There's Saturn underneath there. Titan is a big satellite. I'll say a little bit more about it in a minute. It's covered in haze, has a dense atmosphere, 1.5 bars. Earth is 1 bar. A lot of icy satellites. Enceladus was particularly interesting as it turned out. We didn't quite realize it was going to be, but it was. And it sort of was also, when we found out, was the death sentence for the spacecraft, yeah? And then here's where these things are. Titan's way out there. Pretty much Titan's almost out to where the Saturnian magnetic field begins to balance the interplanetary medium, or solar wind, which is about 20 Saturn radii. Saturn, like Earth or Jupiter or any planet with an intrinsic field, or a pulsar, has a magnetosphere, where the plasma tends to go around with the planet and stands off the flow, external flow, which tends to go around it. And then there is Enceladus. And Enceladus turns out to be quite active. It's pumping all sorts of stuff out into the whole magnetosphere, in fact, and helps determine the structure of the magnetosphere. It's not just protons and electrons. It is also a lot of water ions, H2O plus, H3O plus, O plus, OH plus, which affects the magnetospheric dynamics and also generates energetic particles out here, which impacts some of the satellites. Okay, Titan, big satellite, N2 mainly, but a few percent methane, which is interesting. Surface pressure, pretty high, but it's cold. So the stuff actually stays there. If it was Earth's temperature, well, most of it would have been lost over geological time. Covered in clouds and haze. It has a complex chemistry, as it turns out. I might as well get the factual part in now. Enceladus. It's in the inner part of the system at only about 4 Saturn radii. It's only a few hundred kilometers across. It's basically a chunk of ice. But it turns out it's not just ice. There is evidently a liquid water ocean underneath, or sea, sort of like the Ross Ice Shelf. And there are crevices which are spewing out water vapor and ice grains. So that was what was exciting. The average in the north is pretty cold, 77, but if you go to the southern hemisphere where the crevices are, you can look in the infrared. It's a much hotter region. So we have infrared tells us that. Okay, there's a visible image of the venting crevices there. What you're really looking at is basically solar light scattered off the ice grains, but there's water gas as well. And there you can see the crevices that are emitting the water vapor. And you could track the emission is really right associated with these crevices. Mass spectrometer. We went through the plume, shot right through the plume, also shot through the upper atmosphere of Titan, and we got a mass spectrum. Won't linger. Big peak at 18. Water, H2O. But not just water, 17, because in a neutral mass spectrometer, you have a cracking pattern. Go ask the chemists about it, yeah? You ionize the neutral gas, because you've got to ionize it to put it through the ion optics. And so E plus H2O won't just give you H2O plus, it'll give you OH plus and O plus. So, and it helps you identify the species. It wasn't a very good mass spectrometer because it had a mass resolution of about 0.2 Daltons or 0.2 AMU. Really good ones, are down to 10 to the minus 4, but they're the size of this table or something too. Ours was this big, used a few watts, so you're not going to get a big one out there. And CO2, and some organics, which, interesting. Here's benzene, So the model that was then developed was a rocky core, silicate core, and some of the dust measurements showed some evidence of sodium and chlorine in some of the grains, not all of them. A liquid ocean underneath, or at least a large sea, at least in the southern hemisphere, and some heating of this, which sort of almost like volcanism, but with water, where the stuff leaks up to the surface and goes out. Now, what is the heat source? Thought to be mainly due to tidal heating by a satellite resonance of Mimas, which is going around inside, and Enceladus, so continually being squeezed back and forth, which causes internal heating. But once they realized that there was liquid water, a rock core, there's some evidence of H2, there's some salts in there, that is actually a fairly friendly environment for organisms. Doesn't mean any are there. You can't believe all the NASA hype, okay? they'll make a big whoop to do over this. But it would not be a terrible environment. At that point, they say, "Ooh, we got to leave this alone." Okay. So then the worry becomes, what happens when we lose our thruster? Because our RTGs are fine, but the thruster gases are going down. We'll lose control. We can't do anything about it. It might crash into Enceladus at some point. Yeah. Well, planetary protection or something. So at that point, they began to plot. At least some people began to plot the death of the spacecraft. Yeah. I'm not sure. I don't want to be cavalier, but I wasn't too worried about it. Yeah. I should gotta be a little careful. I'm teaching Astronomy 394 in the fall. I have to develop a better attitude towards external life. Okay. We had to protect this baby. Okay. There's Titan, haze layers. It's like Los Angeles gone amok. Okay. On a bad day, bad smog day. 50 kilometers, 30 miles worth of haze layers. Yeah. Hard to see the surface in the visible. Maybe certain bands you can occasionally get a look at it. That's why the spacecraft have a radar, so you can see the surface. This is almost the scale. A lower atmosphere. I was interested in the upper atmosphere that the spacecraft went through, the exosphere. I was interested in how this upper atmosphere interacted with the external magnetosphere, the electrodynamics. Because a lot of the chemistry was driven by solar radiation coming in, but energetic particles coming in. Basically, you dissociate the methane and ionize the methane in the N2, and thus create chemical radicals and initiate chemical change. So it's all linked. Energy in, chemical gunk out. And the effects go the other way. You affect the magnetosphere. Oh, that's a reasonable view to scale roughly of how the spacecraft encountered it. You didn't, you get as low as you can without endangering the spacecraft. And you could see quite a bit. Okay, our first profiles, again, I'm running a little low on time here, showing some of the first ones at the beginning, but the later ones qualitatively did not look different, okay? Quantitatively, we said how did it depend on latitude, longitude, solar activity, blah, 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 and do studies of this and that. But hey, you had methane, went down with altitude. As you would expect, our atmospheric pressure in our atmosphere goes down with some scale height. It did. Depends on the temperature and the gravitational acceleration. Hydrostatic equilibrium. It works. And here's the methane. And there was a whole bunch of minor species down here too. Minor but important. Associated with how you broke these guys up. This is the first set of ion measurements. It's a little obscure because not much information is put up. That's measured at 3 different altitudes. Far up, and the one at top measured close. And that's the ion spectrum. We had neutral spectrum and ion spectrum. This is actually by paper in GRL by myself back there. And the key point of this is that it's not simple. You would expect with the methane and the N2, well, here's CH5 plus, here's CH4 plus. It's not all CH4 plus. You would expect a lot of N2 plus, and there's a lot of mass 28, except it's not N2 plus. It's HCNH plus because of the chemistry. So what you're seeing is families of species that develop out of the simplest species, and there's a separation by mass 12 and 14. That's carbon. So you got C species, C2 species, C3 species, all the way on up. You're building chemical chains, okay? You're doing organic chemistry. At which point I wasn't entirely thrilled. I took one chemistry course that physics majors had to take as an undergraduate, and I was not, I did okay. I did okay, we'll leave it at that, okay? So I got at this time, our team was pretty interdisciplinary. These whole NASA missions are. Ned Keller, who was an undergraduate chemistry major, but got a PhD in physics. We used that knowledge, okay? Our team had a couple people really familiar with chemistry, I was more into the electrodynamics, but you want to be part of the action. So I got a book called Organic Chemistry for Dummies. yeah, that I thumbed through, So at least know the names of these suckers, okay? And now I know the difference between an ethane and an ethylene and an acetylene, and although it's beginning to fade, so that was interesting. That's something that Ned and I put together with some other team members. She was a team member, a French chemist, and that's oversimplified, as it turns out. It's showing that you start with N2 and methane, and then you begin to develop the chemistry. And it keeps going and going and going. But the trouble is, beyond this point, it's hard to get this specific. You really get into unknown chemistry. Oh, a more recent thing, Hadi Madani, people might remember, he was even some of the grad students. He's got his degree here, last year. He got hooded. And what we did, because the mission had lasted long enough, we were able to distinguish the ion densities between low solar activity and high solar activity and look at the differences in different Solozhenitsyn angles. So this is some of the details that will bore people not in the field silly, but yet does have significance. So I'm going to pass over that, but Hadi did a good job on that. But the general idea of this was that you put in energy, energetic particles, sunlight, N2, you dissociate, you ionize, and you begin to develop things. And in these specters, there was benzene. That's a ring. You begin to attach rings, and you build up, tholins. That was Carl Sagan was wild about these things, and people put gunk in little glass containers of the early Earth and zap it. You get stuff like this. You build organics. Or if you're into interstellar media, interstellar clouds, you see these things. You see PAHs, polycyclic aromatic hydrocarbons, toluene, and other things built up by benzene rings. The chemical schemes and data that we use are essentially the same ones that the interstellar chemists use. It really is the same game as in the interstellar medium or molecular clouds. But it's closer to home. And you can actually send a mass spectrometer to it. Okay, quickly, the probe. The probe didn't see anything till it got below the haze layers. So at about 100 kilometers or so, it got below the haze layers, and it began to see things like this. Sort of channels, dry channels, as if there was liquid something running. When the probe hit the surface, it saw this. It was down in near the equatorial region, and it looked. This is about 3 or 4 inches across. If you're looking at it, you can see the horizon out there. They saw really what those are is chunks of water ice, which are like rocks, eroded by some liquid and coated with sort of a dielectric gunk. Okay, that continually sort of drifts down. But if you go up to higher latitudes, in this case, where is seasonally dependent, in this case, the northern hemisphere, the radar, which was mapping out altitudes, everything, saw some regions with specular reflection. It did some work. That is liquid methane. Might be a little liquid ethane in there, ethane C2H6. Liquid methane, ethane. You can see the spectacular reflections. You can see the deep areas, shallow areas. There are liquid methane clouds and icy methane clouds. There's precipitation. There are lakes. There's a whole cycle, like the Earth's hydrological cycle, but it's in methane. Okay, now we approach the end. So fine, it did a lot of stuff. I did, a whole bunch of good magnetospheric stuff, Saturn gravity stuff. You could, there are books on these things. I don't have time to do all that. I focus on what, interests me, okay? But there was a lot that was interesting. Engines fired about a year ago to change the orbit from just encountering Titan to changing it to put the periapsis closer to the planet. First into the F ring and then even closer. And to make it, to increase the inclination from more of an equatorial orbit to a little more of a polar orbit. And then at the end, they were about 17 orbits that threaded about a 5,000 kilometer gap. That's 10% of the Saturn radius between the inner ring that we could tell is the inner ring and the top of the atmosphere in order to make in situ measurements there. And the last pass was deep enough on purpose that the spacecraft was lost. So that is, this was some projections from beforehand, but it's pretty close. So what you see here are the rings and a little, someone sketched in the magnetic field lines, because at least to some of us that was of interest, okay? And some of these 17 trajectories, where they're going to go in that region. And the last one, which ka-chunk, you know, goes right into the drink there. So and this was one of our planning documents of where the different things were and what we thought we could earn. So this is the spacecraft. This is what's called the tumble level. This is the inner edge of the D ring. There's thought to be a particularly dusty band here. As it turns out, there are at least small grains turned out through the whole area, as it turned out, but not enough to damage the spacecraft, but they were seen. And the orbits were numbered, D17. And the trick is, what is the neutral and ion environment in this region? I'll leave it at that, because we're looking for different things. Part of the thing is there were some expectations that some of the ring stuff near the equator might be coming in to the top of the atmosphere and affecting it. There was evidence in some of the earlier measurements of the electron density that something like that had to be true because of the densities of the ions in Saturn's ionosphere were not what you would expect for a pure H2 type atmosphere. There had to be something else. Turned out there was a lot more than that. But if that's going to happen, anything from the rings will be moving at the Keplerian speeds. It will come into the atmosphere, which is co-rotating with the planet. So there's about a 15 kilometer per second velocity gap that has to be matched somehow to engage the two together. That's still not fully understood how that happens. In the old style terminology, for those who even remember clutches, anyone here remember what a clutch is? Okay, a few people, yes. The engine had a gear to the shaft, and somehow the clutch is in the middle here, okay? That has to adjust those two speeds. And that is actually under active investigation right now. And in fact, that's one of the things, I don't know if he's here, I won't comment if he's not. Oliver Hamill, my postdoc, is interested in those issues. Yeah? So this is just another diagram of some of these encounters that I put together a diagram in September showing the magnetic fields. The dipoles are a little offset. The ring plane is going up this way, center Saturn is this way, showing where some of these orbits are. Closest approach in the southern hemisphere here. I don't show the last one. So they come at different altitudes, and we're basically exploring the latitude structure, the altitude structure in this region, trying to make sense of it. Oh, that was from about 38 years ago. That's the sort of data we had until this first issue data, because until this point it was all remote data till last September. And that just shows that we did measure electron densities. This is electron density is about 30,000 in terms of thousands of kilometers above the cloud tops of Saturn, 1,000, 2,000, 3,000, 4,000. So compared to Earth, this is about the size of Earth. It's a very extensive ionosphere because it's a big planet. Earth's ionosphere extends between about 100 and 400 kilometers. Reflects the radio waves and everything. Yeah? This was taken by what's called radio occultation. The Pioneer 11, and we got some from Voyager, we got some from Cassini, goes behind the planet. The radio signal, you basically is a refractive medium because it's a plasma. And from the index of refraction, you deduce the electron density. You deduce the plasma frequency, which gives you the electron density. And it turned out the simple models were actually predicting things up here at 1 million, 2 orders of magnitude high. So even back then, we realized something's fishy, okay? We need, it can't be just H2 and H. There's got to be some other stuff absorbing it. So, ended up way down there. Okay, this is a spectrum, neutral spectrum of the upper atmosphere, one of them. And benign the time. Surprise! Mass 2. Look at, orders of, 2 orders of magnitude above everything else. Yeah, we were shocked. Molecular hydrogen, no, we weren't shocked, okay? We knew the outer planets are mainly molecular hydrogen, okay? And there's helium. Not surprising. Okay, there's helium down there, about 10%. Actually, less than 10%, but a little tricky there. We're above what's called the mixing layer. So the helium abundance is less than what you would expect. But what was not, we still expected a little water here. Here's the water peak. We actually expected more water because the rings are mainly water ice. What we did not expect was all this other gunk. I don't know why we're surprised. We saw this more complex stuff in Enceladus. Titan, we expected it. It was not shocking, The details were a little puzzling, but Enceladus we saw organics. What surprised us was all this other gunk, coming in there. And it still has not been explained how the rings have so much of this non-ice, water ice gunk. That is not understood. But this is evidence for that. Oh, here's our friend benzene again, okay? Always popping up, A lot of methane again coming in there. So, now there was a little worry, is it contaminant, left over from Titan? We don't think so, because there's independent ion evidence that you should have these other species too, which are really from 2 very different sets of measurements. And it's the ion measurements one that we at KU here have been worried about. It's a different set. This is just what we think might be the methane volume mixing ratio. It depends on height, and it also depends on latitude. So the middle latitude Saturn upper atmosphere is going to be quite different from the equatorial region. It'll be much less affected by the rings. The polar regions will be affected by the aurora because those energetic particles come in. So there's really, in some ways, 3 different Saturn upper atmospheres, ionospheres, depending where you are. Low latitude, tropical if you wish, mid latitude, and polar. The processes are not identical. And we're trying now to quantify these fluxes because it actually puts a little bit of a limit on the lifetime of at least the inner rings. If you add all this up, and really it's not that much, it's a few kilograms per second, but it does limit what your rings are doing. The rings are probably not a permanent feature. Things broke up, last a few tens of millions of years, and gradually they are getting ejected some material or dumped into the atmosphere with this sort of contamination until you have another little satellite of a few kilometers break up and form new rings. So the trick is, how is this happening? Okay, now this lovely diagram is what I've really been working on. And you think I could have, and a couple others of us have done a better job of making it more user-friendly, yeah, I suppose so. I do have a simplifying thing. So this is for one pass. We had about 3 passes for the ions that are this good. So it is really a function of time. This is a passage of the spacecraft. This is when it got closest to Saturn. This is when it went through the ring plane, not quite the same place. What you're seeing here is the total ionospheric electron density, measured in 2 ways, with a Langmuir probe, basically a little thing stuck out there where you change the voltage and you measure the current. Very simple. Plasma instrument, used all the time in labs. The other one just from radio measurements, looking at the frequency of the what are called upper hybrid resonances. You're basically looking at the plasma frequency. Actually, you're looking at the plasma frequency square root of the plasma frequency squared plus the ion gyre radius squared. But it's the same thing. No, electron gyre radius, gyre frequency squared. But it gives you, and they agree. And you're getting it peaking up here, not too different than what you saw remotely for many years, at about 10,000. But previously we thought it was mainly, but now we're measuring light ion composition. We see protons. Our instrument sees the protons here, and at large distances it's mainly protons. They have a long chemical lifetime. H3 plus ions. Oh, here's H2 plus ions. Not a lot of those. Why? Because H2 plus reacts with H2 very rapidly and it forms H3 plus. The original thought was the H3 plus ions would recombine with electrons pretty rapidly and the main species would be H3 plus. Wrong. There's a missing species in here, what I call gap. Okay? Now you could say, well, why didn't we measure the gap species? Well, there's a little problem. On Titan, the instrument measured ion species up to 99 Daltons, 99 mass units. We couldn't go past 8 on Saturn. On Titan, the spacecraft was moving 6 kilometers per second. And what happens is the ions come in, you direct them with the ion optics. They have to make a turn with some quadrupole lens and down into the mass analyzer. At Saturn, because we never thought we were going to measure Saturn until the embargo people said you can't, you got to die at some point. They wanted to kill this. They want to pay for a new Europa Clipper mission. They got to finish paying for James Webb. You know, they didn't want to pay for this anymore. I think that's the real reason. It had nothing to do with protection of anything. You know, that's the cynical view. Okay, so it was not designed for that. It encounters at 32 kilometers per second. That's 6 times the speed or 36 times the kinetic energy. Well, what happened was the ions come in with the kinetic energy, and we have a maximum high voltage supply limit, about 20,000. Never could make the turn. You can't make the turn if they're heavier than 8 AMU. But no problem. We have some knowledge of chemistry developed over years in my single undergraduate course. You know, that tells us what to do with these things. You know, and there's some complicated models. One of my contributions was to make it simple, because some on the project would say oversimple, but I like simple. So here's H2, here's H, the neutrals. You got photons, mainly photons in the equator. There's no aurora. They produces H2 plus, and about 10% of the time H plus. H2 plus reacts, produces H3 plus. We thought this was going to be, these two would be the big ions. Well, we have to postulate that there are other ion neutrals, and we know it because we saw a bunch of gunk there. That will react with this and remove them and produce other heavy molecular ion species. Advantage of those are those undergo a very rapid, what's called the social recombination reaction. They find the electron, and that's a fast rate coefficient. About 10,000 times faster than what H plus could do with radiative recombination. So it solves it. In fact, what we did is we went backwards. We deduced the mixing ratios of these things, and they actually agreed, not bad, with the neutral measurements, which is good, because there was a little suspicion of those because of instrument. So the two very independent, I'm going to skip a lot of this, two very independent sets of measurements for the neutrals and ions do tend to agree. There is ring contamination. It's not some instrumental artifact is what it tells us. Okay, yeah, yeah, fine. Details. Oh, some of the last data. This is a methane mixing ratio. Forget this, look at this. This is altitude. These are, and because it depends a little bit on longitude, the mixing ratio is down to an altitude above the cloud tops about 1,700 kilometers. The ion spectrum I showed was 288. It was this one right here. But this is the last one. It went down actually about 200 kilometers deeper. Because that, you know, and then it didn't come out either. You know, if you look carefully, you can see some go in at one latitude to come out at the other latitude. This was the one-way trip, and that's as far as it got. Oh, never mind. We think a lot of the stuff is coming from a little ringlet satellite. And might be somewhat time dependent. And some of Oliver Hamel's work on dust ablation. Some of it is gas coming in, some of it we think is very small grains coming in, which vaporize. And that's some of his models. So let's talk about the end, because I got about 2 minutes, and it's time to do the end. The entry was on September 15th, 2018. So initially, again, we had a whole long week meeting before them because there was a lot of arguments over this stuff, what we were seeing. And the ring people had their own arguments and a lot of interesting measurements of the gravitational moments too, which I listened to but didn't quite understand. You know, what is the internal structure of Jupiter, or the higher moments of the magnetic field. So we had different group meetings depending on your interests. And then the last day we sort of broke up the meetings to go at about 3 a.m. again. I don't know why it's always in the middle of the night. Actually, it was about 5 a.m. Pasadena time, but you had to get up earlier to go there to see the entry. So what happened at the end is the thrusters, as it came in deep, tried to maintain the attitude of the high gain antenna onto the Earth because it was real-time data at that point. Usually, most of it was always put on solid-state recorders and sent back at convenient time to the big dishes. They have these 60-meter dishes out in Goldstone to get the signal. Well, in this case, you can't store the data. They had to set up the real-time link as it went in, and the thrusters tried to maintain attitude control. They were going about 10% of the time as the previous steps, but as it went down the other 200 kilometers, the thrusters started firing more and more frequently. Finally, after about a minute, they were continually firing, trying to hold the orientation against the torque, and finally they couldn't do it. It lost the signal, and they estimate about a minute or two later, pieces would start breaking off the spacecraft, but you know, you're not going to get evidence of that. So it happened at there. And of course, we all got together. Yeah. Here's an image of the control room during that time. Again, a bunch of us were actually out at the JPL campus looking at this on closed circuit TV, you know? And there we were all staring at the carrier signal. And it lasted about 20 seconds more than we thought. They said, oh, it's going to go now. Oh, still there, hey. But finally it did go in 20 seconds. Got about 100 kilometers deeper than we thought for whatever reason. You know, and it disappeared. You know, no drinking or partying. I mean, I got in my rental car after a couple hours and drove through the traffic back to Lax. Yeah.
Were there any failures?
Well, some of the operational people have been dealing with this for many, many years in the JPL, and they were a little choked up. Scientists were jerks. We just went home, you know. We had papers to write, yeah. We had new missions. We were all thinking, what new mission? So I'm writing a proposal to get onto the Juno mission, yeah. You know, we're opportunists, yeah. You know, what could I say, yeah. I was sorry to see it go. It was really very, you know, it was a good chunk of my career, okay? It was a lot of PhD dissertations. There's at least 6 students here that some aspects of it were in their PhD dissertations, you know? No, so I felt bad, actually, I did. I shouldn't exaggerate that I didn't, but I still had to drive to the airport, you know? So I think that was it. That's one of these group photos where you each get 2 pixels. Yeah, yeah.
Yep.
What? You're not good. No wait. I don't think you're going to see me in there.
There's a circle.
Oh, I forgot I put that in there. Okay, yeah, I'm in there. We're in the shades and the shiny head there. Yeah. Okay, thank you, Joe. The last ring image. That was one of the very last ring images, and there is a movie put together from one of the passages through the ring gap. You know, as you're coming in, you see him, and then you see him edge on, and you come out. And that will, yeah, so there we are, bye-bye rings. Okay, more science, which I'm not going to talk about. We'll end there.
Thank you very much for the interesting colloquium. Now it's time for questions or comments.
Would you like to go back, and if so, why?
Would I like to go back where?
Saturn.
You mean
Spacecraft.
If
Well, the
they give you-
spacecraft,
if they
not
give
not
you
personally.
I want to know if they give you
Personally,
another
yes, Steve, I have never
20
been in Europe.
billion
No, not one of these Martian types.
They give you another $20 billion, you know, inflation. Is there anything that you
Actually,
would still be interesting?
there are still interesting things in the polar regions of Saturn, in my opinion. You know, the auroral interactions. There are interesting things on Titan that not so much my expertise, but I think people would be interested in going much deeper. I think it would be nice to get down and delve into Enceladus a bit more. Again, it would not be my expertise. So I could, you know, I could see some interesting things in a more general scientific thing. I think it would be interesting to plunk something in these methane lakes, you know? You float around and do stuff. Do I think it's going to happen in the current climate? No, because going out there is very expensive. And the next thing is going to be even worse because you do have to design balloons or little boaty things or something to float around, you know? It's very expensive, yeah? But I think there is interesting stuff out there to do that we do not know, yeah? We wish we had a better mass spectrometer. There's a lot more we could have done with the isotopes to learn a little bit more about the origins of the atmosphere if we did better isotope ratios. But we would need a M over delta M not of a couple hundred. We'd need, you know, some tens of thousands like you've got down the hall here, and find a way of designing it. You could actually get it on a spacecraft in an affordable fashion, you know? Now, in my own particular areas, would we want to, I'd say what they're going to do next is not an unreasonable one. They're going to go to Europa in the Jupiter system. It is closer. We also know it has an undersea ocean. It might not have plumes, so I think that's not a bad next thing to do. In this sense, I don't disagree with the NASA goals. I'm a little freer because, let's be honest, I'm not at the beginning of my career. I'm not saying it's at the very end. I'm not quite like Cassini yet, but I'm, you know, don't stare at me, Hume, you know? Makes me nervous, okay?
That's my job, right?
But yes, so I don't have to focus on just what is my own little niche. But I think the Europa thing could be very interesting. I think some of this astrobiology thing could be interesting, you know, in spite of my, you know, remarks about contaminated Enceladus. You know, I think, yeah, actually it would be interesting to see what would happen if we put some microbes there. Would they survive, yeah? Well, I mean, you got to admit, wouldn't that occur to you to try that? Yeah, I mean, once you really convince yourself nothing intrinsic was there, you know?
Good gypsy moths there. What could go wrong?
What?
So many opportunities to do that on the Earth.
Yeah. Yeah, we've done a pretty good number on our own planet. Let's move out and spread the wealth, so to speak. So I think there, yes, in the Saturn, interesting stuff, but I think probably going to be a little closer to home. Jupiter might be a little better. It's a price tag too, you know?
Yes, one more question.
Okay, so I'm not a physicist, so I can ask this question. Can you fly through Saturn?
Fly through Saturn.
What the density is, are we talking black hole crushing?
Yeah, it would be pretty crushing, yes.
Have a really, really, really solid state.
Well, you know, the pressure gets higher and higher and higher. At some point, the molecular hydrogen becomes metallic. You know?
So plasma.
Now, yeah, it's just, I mean, it's,
Okay.
no. I think we could get much further down than we did with Cassini by not plunging in at 32 kilometers per second. If you ease your way in, you could go deeper and deeper and deeper. But there's going to come a point, you know, like the Galileo probe in Jupiter went much deeper than Cassini did. I mean, Cassini's problem was it was moving at basically escape speed almost for Saturn. It was plowing in there. You know, the dynamic pressure goes as rho v squared. You know, that v squared was pretty tremendous. On Galileo, they did manage to buffer it, throw chutes out, and have drag, and so we can get it a lot deeper. That might be interesting. Yeah, it would be interesting to do that again on Jupiter, because unfortunately we got to a really low water area where Galileo probe went down. Another Jupiter probe to go deep into the cloud layers would help in figuring out how that part of the solar system formed as well. So there's a lot of things you could do. The trouble with the outer solar system, they all come with a high price tag. To do them, Juno worked with solar panels, but it was pretty dicey. Most of them need RTGs, and we're running a little low with the plutonium isotope we need for that. You know, because it'll what happened to the weapons program. On the other hand, that part could turn around. We might be reinvigorating that, and there'll be leftover plutonium, you know, for RTGs. But that's a pretty high price to supply your power supplies for space missions.
Always a silver lining.
You got to be opportunistic, Cube.
Let's thanks Professor
Okay.
Craven.